I want to look at 2 or 3 application problems today. One comes back from chapter 2 on page 70. From section 2.4. It's an application problem. We want to somehow model the equation on some mathematical equation that we already know and to be able to solve. We have an illustration of a chain that is falling, and you want to calculate a couple of things. You want to calculate the distance of how much of the chain is falling with its velocity, what rate the chain is falling from this table, this platform edge. They give us a model here, this differential equation, and from there we want to try to put the pieces together to be able to solve for the velocity. X denotes the length of the chain overhanging the table. It does not include the amount of chain that's on top of the table. And suppose that the length of the overhanging chain is 3 feet. That's just the initial length there. And the weight of the chain is 2 pounds per feet, and that the positive direction is downward. Part A, rewrite this model in differential form. Use something that we already know to be able to find an explicit solution for V of t, basically to isolate V, to try to solve it. Well, let's see. So I'm going to take this equation and see if I can. That equation is x times v times dv over dx plus v squared is equal to 32x. Hopefully we had a couple minutes to look at this. This model tries to mimic what type of equation? Bernoulli? Good. So let's see if we can write it in that form. First, let's divide through by the x. And so when we do that, we have v dv dx plus 1 over x v squared is equal to 32. Now, to really see Bernoulli, let's go ahead and divide through by the v to see it, and then from there we could solve it. So we have dv over dx plus 1 over x v is equal to 32 all over v. So this is Bernoulli. Typically we have Bernoulli in y, but this is Bernoulli in v. So we say that the term that we have on the right side, we need to somehow run that through the entire equation. And doing that, we'll get back to this guy right here. But I just wanted you to see that this is the Bernoulli form. So multiplying through by the v, we get this form here. And so now what we do is to let u equal to the v squared. Take the derivative of both sides. So we have u prime is equal to 2v v prime. So we have v prime here, so 1/2 u prime would represent the v prime. So this implies then that 1/2 u prime is equal to v prime. So I replace the v prime, that is v dv over dx, with 1/2 u prime. So this is 1/2 u prime plus 1 over x times u, because the v squared becomes u, is equal to 32. Multiply everything by the 2, and then it becomes a linear equation. So u prime plus 2 over x times u is equal to 64. Do you see that the integrating factor would be x squared? The integrating factor mu is e to the integral of 2 over x dx. So that's e to the 2 times the natural log of x. And that's, you see that that's now x squared, right? E to the natural log of x squared. Now do you see it that this is x squared? You still haven't said anything. Okay. So we multiply everything through by the integrating factor. You can skip this step if you want. We said that the left side is automatically the derivative of the product of the integrating factor and the dependent variable, which is u, is equal to this right side, which is the 64 times the integrating factor x squared. Integrate both sides. So if you will, we can just go right to it. This is x squared u is equal to 64x to the third over 3 plus some constant. Divide both sides by x squared. So this implies that u is 64x over 3 plus c all over x squared. But the u was, that was v squared, right? So that is, this is v squared is equal to 64x all over 3 plus c over x squared. Solving for v is the square root of 64x over 3 plus c over x squared. To solve for c, we need to know two things: the initial velocity, and at the initial velocity, what is the length of x. It tells us that at rest, the length of x is 3 feet, right? So at v equal to 0, x is equal to 3 feet. So we have 0 is equal to the square root of 64 times 3 all over 3 plus c over 9. That implies that c over 9 is equal to negative 64. So this implies that c is equal to negative 9 times 64. So the velocity is the square root of 64 over x times 3 minus 9 times 64 all over x squared. You could factor out an 8, so this is 8 times the square root of x over 3 minus 9 over x squared. So then it says determine the velocity with which the chain leaves the platform. So find V. The key is, what's the value of x? When x is equal to a portion, start back at the beginning, a portion of a uniform chain of length 8 feet is loosely coiled. So when x is equal to 8 feet. Right. You can check my math. I think somewhere around 12.71 feet. Give or take a little bit. Okay. Any questions? Yes, we're looking for the velocity, excuse me. Yes. 12.71 feet per second. Yes, thank you. Okay, now let me get back to 3.1. There was another problem there that I thought was interesting. Let me delete this page. In section 3.1, I think the last problem that I worked was number 36, the last one that I did. So this is 37, which somewhat flows from number 36. So repeat problem 36, but this time assume that air resistance is proportional. So in number 36, it said there was no air resistance, which is most likely not really practical and possible. So here we have a problem that is more so close to reality. So the air resistance is proportional to its instantaneous velocity. It stands to reason that the maximum height attained by the cannonball must be less than what we got back in problem 36. In problem 36, we got a height of 1,406 and some change, right, feet. Show this by supposing that the constant of proportionality K is 0.0025. Modify slightly the DE in problem 35, and I put 35 here. So the DE that we're working with is this guy. So we're going to replace that K here with 0.0025, right? And we're going to divide through by the mass just to get dV over dt by itself. So hopefully we can solve it by matching it with some kind of differential equation that we've looked at already. And the acceleration due to gravity is 32 feet per second squared. Okay. So we have dv over dt is equal to g minus k over m times v. Let g equal to 32 feet per second squared. K is given here to be 0.0025. What is the mass? For the mass, number 36 says suppose a small cannonball weighing 18 pounds, right? That's the weight. So the weight was 18 pounds. It's not the mass. We have to calculate the mass from the weight. So here, if the weight is said to be the mass times the acceleration due to gravity, right? So this is, it says it's 16 pounds. So the mass is 16 divided by 32, 0.5. So we're going to put that in for m. So we have dv over dt is equal to 32 minus 0.0025 divided by 0.5 times v. This implies that dv over dt is equal to 32 minus 0.05? Let's make sure got the decimal in the right spot. .005, yes. Let's write this one more way. This is dv over dt plus 0.005v is equal to 32. Okay. So what type of equation that is? Linear, right? Good. So, let me see if I can set it up for you and give you just about 10 minutes to see if you can finish it. It's a linear differential equation, so you got to find the integrating factor, right? Find the integrating factor, and then from there you want to be able to solve for v. You're going to get v of t by itself. That'll give you the equation for the velocity. Once you have the equation for the velocity, you want to find the total time. To get the total time, you're going to set the velocity equal to 0 to find t. Okay? It's that t, that time, that you will use to be able to solve for the height, the maximum height. Now, how do you get the height or the position equation from the velocity equation? Because remember, you're going to solve for the velocity once you use the linear equation model, right? Get the integrating factor and do that process. How do you get the position equation from velocity? It's integrated, right? So you have that v of t sitting by itself, equal to whatever. Integrate that, that'll give you the position vector. And then you take that time that you calculated from setting v equal to 0, take that time, plug it in, you should get it. All right? I'll give you a few minutes for that. I got some work going on upstairs, so kind of back and forth. So I'll be right back. Let me write that down so make sure you got the process. Use the integrating, that's number one, factor to solve for V. Secondly, set V equal to 0 and solve for T. Integrate the equation V of t to solve for S of t. Use the time from 2 to solve for S of t. And this is an odd problem, so you'll be able to look in the back of the book to check your answer. So give you about 10 minutes for that, and then I'll come back and look at one more problem, and then I'll be finished for today. How we looking? Hmm? All right. Let's see. If I want you to spend some time with that one, I need you to be able to work it. Let me set up another problem, and then we'll go. Have you ever heard of the linguistic equation? It's a very strong mathematical model. It tries to improve the population growth or decay differential equation. Um, there was a scientist, mathematician by the name of Verhurst, who worked on the population growth model and improved it. And a lot of the science of species in the oceans utilize this particular model. This is in section 3.2. It has very strong application of which you have seen before. Let's see if I can set it up and let you finish it, and then we'll go. The number N of T of supermarkets throughout the country that are using a computerized checkout system is described by the initial value problem. Use the phase portrait concept of section 2.1. Did not cover that, but let me go ahead and just talk about it. Doesn't take no more than about maybe 3 or 4 minutes to explain that. To predict how many supermarkets are expected to adopt a new procedure for a long of the given initial value problem. No need to do that. But more importantly, part B, solve the initial value problem and then use a graphing utility. No need to use the graphing utility, just solve the DE. Let T equal to 10 and then calculate the number capital N of T. Just a statement on the so-called phased portrait. Here for the phase portraits, we would like to determine a basic graph pattern to illustrate the intervals of which the DE is increasing or decreasing with respect to a critical point. The critical point is simply just take the differential equation. If you have the derivative by itself, which we do in this particular problem, you just set the other side equal to 0, and you solve for the variables, and those will give you so-called critical points. Not the same idea of critical point or critical value for a first derivative. if you will. A little bit different, but this helps us to get an idea of what we call stability or instability of the differential equation. So here's a differential equation. So just set the right side equal to 0 and just solve for n. So this was n, set n times 1 minus 0.0005n equal to 0. This implies that n is 0 and 1 minus 0.0005n equal to 0. That second one, if we solve for n is equal to 1 all over 0.0005. That's 2,000. So for the so-called phase portrait, we'll just take this this vertical number line, and we're going to just label these critical values. So 0 and 2,000. Just pick any point on each interval to determine the sign of the derivative, whether it's positive or negative. That just lets us know that the derivative is going to be increasing if it's a plus sign, and where it's decreasing for a negative sign. So say, for example, if we pick a value greater than 200 and plug it in here. So if we take, let's say, 2,000, greater than 2,000, excuse me. If you take 3,000, so this would be positive, and then this would be 1 minus, and this would give us 2,000 times 3,000. It'll be negative times a positive, so this would be negative. So we say here that this is decreasing. Take a value between 0 and 2,000. Let's say, for example, if you take 100, it doesn't matter. So n is 100, it's positive. 1 minus this guy, this would give us positive. So here we'd have increasing. Doesn't really matter what happens less than 0, because we're talking about real term values anyway, right? But if you wanted to check, just for the sake of the chart, let a number be less than 0, which doesn't make sense, right? But if that be the case, if you take a negative value here, put a negative value there, times this would be positive, so we have negative times a positive, we get negative. We say that if the arrows are both pointing to a critical point, we say that at that point it's stable. If you have a critical point, and if the arrows are both pointing away from the critical point, is unstable. If you have a critical value, and if you have one arrow going, well, the arrows are going in opposite directions. So, say, for example, if one is coming in and the other one is going out, or vice versa, then we say that that's semi-stable. The stability gives us the initial clue. Use the phase portrait concept of section 2.1 to predict how many supermarkets are expected to adopt the new procedure over a long period of time. That's going to be where you have stability, and that's going to be at 2,000. Right. So this is the market gain for this particular economic model. So here, n is equal to 2,000. So now it says in part B, solve this differential equation. Now let me set that up. This is dn over dt is equal to n times 1 minus 0.0005. 0005n. I think that's it. Simply separate the variables. Then we can separate the variables for this the linguistic equation. The actual model is dp over dt is equal to p times a minus bp. Here p is n, right? And there the little a is 1 and the little b is 0.0005. So that's the actual model of the of Verhulst. So we separate the variables. So what we have is 1 over n times 1 minus 0.005n dn is equal to dt. Now to solve this particular differential equation, does anybody have an idea? Partial fractions. Perry, right? Nick? Okay, sorry. Okay. I'm going to take y'all picture and put your name by the picture so I can get this thing right. Okay, yes, partial fractions. Oh, by the way, I did not assign a homework problem from 3.2. I'm working on a project for you all, and the project would encompass the information that I'm covering today. So I'm trying to give an introduction to the project that I will give you, something that you can do outside of class. And so what I'm covering will set all that up for you. Okay. So we're going to integrate now this 1 over n times 1 minus 0.0005n is equal to a over n plus b over 1 minus 0.0005n. Multiply both sides by n times the expression 1 minus 0.0005n, and that would imply then that we have 1 is equal to a times the expression 1 minus 0.0005n plus bn. If we let n equal to 0, we get a equal to 1. Letting n equal to, if we set 1 minus 0.0005 n equal to 0, you get n equal to 2,000. So let n equal to 2,000. This implies that b is equal to 1 divided by 2,000. Okay. So now the integral would look like the a over n, excuse me, which a is 1, plus the b, which is 1 over 2,000, all over 1 minus, you can write that, this is n over 2,000. Just get rid of those decimals. This is dn is equal to the integral of dt. Let's clean that up. This is the integral of 1 over n, plus this is 1 over 2,000 minus n. dn is equal to the integral of dt. Now, integrating both sides, we get the natural log absolute value of n. Of course, n is greater than 0 or above that, so we can drop the absolute value signs. This is minus. I hope you see why that's minus the natural log of 2,000 minus n is equal to t plus c sub 1. You see why that's a negative there? Right? Use that u du, right, on that 2,000 minus n, so you get negative, you get du is equal to negative dn. Right? Get everything together and exponentiate both sides, so you end up with n over 2,000 minus n is equal to e to the t times e to the c sub 1. And for this problem and the previous problem, that e to the c sub 1 is very sensitive. You know how before I would just let that equal to c and just go on about our way? Well, with these application problems, you have to take into account e to that constant and just leave it as such. Because if you don't do that for that previous problem that I left you all to do, then you won't get the right result. Okay. And so you want to solve for c sub 1. To do that, they gave an initial condition of n of 0 equal to 1. Right? So when t is 0, n is 1. Okay. You do that, you solve for c sub 1. There it is. Oh, let me go back and see what I had. Right. So we let t equal to 0, so we get just e to the c sub 1, and then let n equal to 1. This is 1 over 1999, right? So this would imply, just write it here, that e to the c sub 1 is equal to 1 over 1999. So we get n over 1 minus, was it 2,000? I'm trying to remember. Minus n is equal to this. We said that e to the c sub 1 was 1 over 999. So just write that 1 over. And that's times e to the t. So we're going to multiply both sides by 2,000 minus n. So n is equal to 1 over 1999 times e to the t. This is times 2,000 minus n. N is equal to e to the t over 1999 times 2,000 minus e to the t times n over 1999. I'm going to get the n's together because I want to be able to just have n expressed explicitly. So this is n plus e to the t times n over 1999 is equal to 2,000 over 1999 times e to the t. This is n times parentheses 1 plus e to the t over 1999 is equal to 2,000 over 1999 times e to the t. I got to divide both sides by 1 plus e to the t over 1999. Let's write this as one term first to make it easier on ourselves. This is 1999 plus e to the t over 1999 is equal to 2,000 over 1999 e to the t. Now divide both sides by this guy right here. So n, or n of t if you will, is equal to the 1999 will go upstairs, cancels out with this guy, so I have left 2,000 times e to the t all over 1999 plus e to the t. Now, can you do this for me? Because I'm 1 minute over. Plug in t to equal to 10, and let's see what you calculate for n of t. So n of 10, because that's where the question is. See what you get on your calculator. If it comes out right, I'm going to be like Eddie Murphy. I'm going to step back and kiss myself. Yeah. Eddie Murphy doing James Brown. But step back, kiss myself. That's it. Thank you. On Wednesday when you come, I'm going to go ahead and start in chapter 4, but I will let you know what the project is for you all to complete. That's going to, here's what I'm trying to do. I'm trying to give you something so that I can add to this test 1 grade to boost that score up. Okay? That's what I'm working on. Thank you.